This video is titled Parametric Curves Part 28. It's part 7 of a subseries about modeling the trajectory of a ball or a projectile in general. In the last video we focused on what does it mean for the velocity vector to be the derivative or rate of change of the position vector, and we will continue to think about this in this current video. In order to do so, we need to think about some things with vectors. First of all, the geometric meaning of scalar/vector multiplication, where you take a number, and let's say it's a positive number, and you multiply it by a vector. If the number is bigger than 1, that makes the vector be longer. If it's between 0 and 1, that makes the vector be shorter. We also need to emphasize vector addition and what that means geometrically. So here's the situation. You might want to pause the video and look this over. We are modeling the trajectory of a ball, only considering the influence of gravity, no air resistance, and we thought about these questions in some previous videos. This program that you see here is called Mathematica. We've been using Mathematica to make animations showing the motion of the ball like this. You can run the animation. So the ball is the big black dot that you see. The curve that it is following is a parabola. That's the trajectory of the ball. We also see some arrows in the picture. First of all, you've got this blue arrow that's starting at the origin and going out to the ball at every instant in time. I paused the animation here at this instant in time. That's about 1.4 seconds into the motion. That blue arrow is called the position vector of the of the ball at that moment in time. It again points from the origin to the ball's location at that moment in time. Excuse me. What about this red arrow? This red arrow, you can see, this red vector is based at the location of the ball at each moment in time. It points in the direction of motion at every moment in time, and it turns out, we've seen that the length of that vector, its norm, is equal to the speed of the motion. That red vector does not stay a constant length, so it is not only changing in direction but also in length. It is shortest when the ball is at the peak of the motion. It doesn't change in length much, but it does change a little bit. What about that dash brown arrow that you see? Well, that's a position vector for the motion as well, but not at the moment in time that we're at here, about 2.67, but rather about a half a second later. In fact, exactly half a second later, because I put a plus 0.5 in this code that made that be the position vector for the motion 1/2 a second later. What we emphasized in the last video was that we wanted to note that this red vector, this red arrow, the velocity vector, almost points in the direction from the tip of the blue arrow to the tip of the brown arrow. And that happens all the time, no matter what spot the ball happens to be in. Another thing I want you to notice that I didn't mention in the last video is that in this case, when this is 0.5 seconds into the future, that red arrow is about twice as long as the distance between the tip of the blue arrow and the tip of the brown arrow. Not exactly, but about twice as long. And that seems to stay constant as well. In other words, if I rescaled that red vector, if I scaled it down, multiplied it by the scalar 1/2, it should almost go from the tip of the blue arrow to the tip of the brown arrow. It wouldn't be the velocity vector anymore, but it would do that approximately. Let's see if that happens. So here's where I make the red arrow in this code. If I multiply this v of b, the velocity vector at time b, by 0.5, that should do what I just mentioned. Again, it's no longer the velocity vector. It's half as long as the velocity vector. It points in the right direction, but it is no longer the velocity vector. You can see if it starts at the tip of the blue arrow, it almost points to the tip of the brown arrow at every moment in time. What if I change the time interval? Instead of 0.5 seconds into the future, I look at 0.25 seconds into the future. Now the brown arrow is closer to the blue arrow. Looks like it's an even better approximation that the red arrow points in the direction between the tip of the blue arrow and the tip of the brown arrow. And what if I again rescale the velocity vector to be 1/4 as long as it is? Now this fact that the red arrow is almost exactly pointing from the tip of the blue arrow to the tip of the brown arrow is even more apparent. This approximation so to speak, is getting better and better the smaller and smaller we make this number. Let's go even further, maybe 0.1 in both spots. A little hard to see here perhaps, but you can trust me, the red arrow, if you were able to draw it more fully, goes from the tip of the blue arrow to very close to the tip of the brown arrow. Not exactly, but very, very close. Basically what I'm trying to say here is that we can generalize this statement that we made in the last video about the derivative of a function f of x representing the rate of change of that function to the vector case. Let me recopy it down here. So let's suppose we have now a vector valued function, an r of t. Let me unboldface all of this, and then I will boldface the vector. So this is a vector valued function that is smooth on its entire domain. What does that mean? Well, basically here it means that it doesn't change suddenly, either by jumping from one spot to another or in sort of a jerky motion. It's smooth on its entire domain, and we have a number, t equals a, in that domain. The value of the derivative of this vector valued function, this position vector, and this is notation that we are using for a position vector. And why did that change to black? I'll change it back to red later. The value of the derivative of that position vector, r of t, at time t equals a, denoted by r prime of a, also denoted by v of a, the velocity vector at time a, is the rate of change of r near t equals a. So I'm just again re-emphasizing these facts in this context of a vector valued function. What does that mean? That means if t, time changes by a small amount, call it delta t, from t equals a, maybe I should mention that would mean 2 time t equals a plus delta t, then the change in r instead of y is well approximated by the product of the derivative, which is the velocity vector, with delta t. And that would be a product of a scalar, a number, delta t, times a vector, v of a. That is, in an approximate equation, delta r, it lets me copy and paste this, delta r is approximately v of a times delta t. And this statement is an analytic expression of the approximation we were observing. Let's go back to 0.25. What do we have here? Stop it at a certain moment in time. V of a times delta t is this red vector. The longer red vector that we initially drew, that was the velocity vector. Delta t here is 0.25. I'm multiplying that scalar by the velocity vector. I'm scaling it down by a factor of 1/4. It is 1/4 as long as the actual velocity vector. That's the right-hand side of this approximate equation here. That's approximately equal to the change in r, the change in the position vector. What's the change in the position vector? That is represented by the arrow that goes from the tip of the blue vector to exactly the tip of the brown vector. Talk about this more in the next video. I'll say it again. Delta r, the change in the position vector over this interval of time, is a vector that goes from the tip of the blue vector, when you put its base at the tip of the blue vector, exactly to the tip of the brown vector. This red vector goes there approximately, not exactly, but it is a good approximation to delta r, and that approximation gets better and better as delta t gets smaller and smaller.